Hello everyone, welcome back to the channel. In this video lecture, we shall solve this problem inversion count, which is a standard interview problem. This problem also repeats in many online coding contests. Let's see what the problem statement is. We're given an array nums of length n, and our task is to find the number of inversion, where an inversion represents two elements in the array such that the first element exists before the second element and the first element is greater than the second element. Let's understand the input and output format. In the input, we will be given an array of n integers, and in the output we have to print one integers which represents the number of inversion. Let's understand the problem statement using an example. Basically, inversion in an array is a pair ij such that I is less than j and element at I is greater than element at j. So this is nums array which contains 4 integers, and these are the inversions that exist in this array. You can see that each of these pairs satisfies this property, that is, first element exists before the second element and the first element is greater than the second element. Hence the answer for this input data is 6. Let's see how we can solve this problem. The naive approach to solve this problem is simply use nested loops, that is, iterate over the array using some pointer I represented by this loop. So this pointer I iterates over the array starting from the first element until the last element, and for each element I start iterating from the next element using another pointer j here and check if element at I is greater than the element at j. If it is the case, then this is an inversion, and finally we return the count. So this count stores the number of inversion. What is the problem with this approach? Although the approach gives right answer, but the time complexity for this approach is quadratic, that is big of n square, and hence it will not work for the input of size 10 raised to the power 5, which is the input size given in the problem. Hence we have to improve upon the time complexity. Okay, so this is the time and space complexity for brute force approach. The space complexity is constant because we are not using any extra space here. So the optimal approach to solve this problem is using merge sort. I hope you know what is merge sort. Merge sort is basically a sorting algorithm which is used to sort arrays, and it works using divide and conquer approach, where we are given an array of n integers. Here we divide this array into two halves, we sort these two halves, and then we merge these arrays to get our final sorted sequence. Here we can see that this step, that is dividing, sorting and merging, is repeated recursively for each array. So here the parent array, we divide it, we form two halves, then we repeat the process for these two halves as well, and so on until we get all elements separated. Then we start merging the elements, and this is where the sorting actually occurs. Finally we have our sorted array. So this algorithm, that is merge sort, works in n log n. Let's see how this algorithm actually works. So this function, that is merge sort function, takes in the array which we want to sort, the starting index of that array and the ending index of the array. That is what this function is saying, okay, sort me the array from this index up until this index. Then this is the base condition, where if we exceed, that is the ending point is less than the starting point. So this is a case where either we end up with no element in our range or we have single element remaining. Then we'll calculate the mid of the array. So initially we calculate the middle element. So in this case we have 7 elements. So we calculate end, that is index 6, start, that is index 0. So we calculate 6 minus 0 by 2, that is 3. So we calculate the mid as 3, that is this element. Then we recursively call this function for this half and for this half. So this represents the left half of the array, this represents the right half of the array, and here we are dividing the array into two parts. So what we are saying, okay, I have divided the array at the middle element. Now I want to do the same for the left part, and I want to do the same for the right part, and so on. This process is, since this is a recursive function, so this process is repeated until we end up at this base case. After that, once we are done with it, we call the merge function. So what this merge function is doing, we know up until here we have divided the array at middle element, and we have a sorted sequence starting from start up until mid, and another sorted sequence starting from mid plus 1 ending at end index. And we want to combine these two sorted sequences. So this is a merging step, and hence we call another function that will merge these two sequences into the original sorted sequence. So this function is taking in the array, taking in the starting index, the middle index where we have parted the arrays, and the ending index of the array. So this is how the merge function is working. It is taking in the array, that is the input array, the left index, the starting index of the array, middle index where we have parted this array, and the ending index of this array. Then we find the length of the first sequence, that is the array starting from left ending at mid, and we find the length of the second sequence, that is from mid to right. Then we declare two auxiliary arrays here of the same size which these two sequences are, and we store the integers of these two sequences which are there in this array into these auxiliary arrays. Then we declare two pointers, pointer I which will point to this array, that is left, and pointer j which will point to this array. So this sequence stores the left half sorted sequence, this sequence stores the right half sorted sequence, and this basically index will be used to fill this array. So this index will be used to point to this array, so that we want to copy the sorted sequences into the original array. So what we are doing here, we have a parent array, we have divided into two parts, we copy the integers into auxiliary arrays, then we want to these two independent arrays, that is L and R, they are sorted, but we want to combine them to make single sorted array. That's why we will use this pointer k which starts from left, because this pointer will be used to point to this array, as this array will store the combined results of these two auxiliary arrays. Let's see how it will be performed. So here you can see that I'm iterating over the first and second arrays. It is saying even if one of the arrays is exhausted, break this loop. If ith element in the first array is less than the jth element in the second array, then we're gonna assign the smaller element first. That's what we are doing here. Otherwise, the smaller element is the jth element in this array, and hence we assign that element at index k, and we increment k by 1. So I'm copying these arrays into the parent array, and here what I'm doing, maybe one of the arrays are exhausted and other array has remaining integers which will be copied to the parent array using these loops, and finally we return the sorted sequence from here. So this is how merge sort function works. So this is the merging step of the merge sort function. Let's see how this can help us to solve our problem of inversion count. So here you can see that this is the modification that I have done. So this is the merging function, that is we are trying to merge the arrays that we have divided, and I initialize a count variable. This will store the number of inversions that we have in the array, and I iterate over these two arrays. So these arrays basically represents the two auxiliary arrays that we declare in the merging step, and the code is same. If the element in the first array, so let's say we are trying to merge these two arrays, so array number 1, array number 2, so this is array L, this is array R. So what I'm saying, okay, the I is pointing here, J is pointing here, and I see and K is pointing at this position. So this is the parent array which we want to fill from these two arrays. Now I see the element at this location is less than the element at this location, hence I store 3 first because I want to store integers in sorted sequence. So that's what I'm doing here, and I increment I by 1. Now I is pointing here and J is still pointing here. Then I compare these two elements, element at I which is 27 and element at J which is 9, and I see the element at J is smaller than the element at I. I is pointing to this integer, j is pointing to this integer, I can see that integer at j is less than the integer at I, and hence I store this integer in the final array. So that's what I'm doing here. And in this is the modification that I have performed, where in the count I'm incrementing the answer by n minus I. What does this represents? I'm saying that the integer at location I is greater than the integer at location j, which is this, then definitely all the integers to the left of I here in this array, so this array has a length of n, and all these integers that are to the right of this integer will be greater than the integer at I, because these are sorted arrays, and hence all of them are greater than the integer at j, because integer at j is less than the integer at I. Therefore all these three integers will make a inversion with this integer, and hence there will be three inversions which will be contributed by these three integers. And how would I know how many integers are there? And that's what I am adding at this point. And then I'm incrementing j by 1 because I have dealt with this integer, I have stored it, and finally I increment my pointer k to store the integer at next location. Let's discuss the time and space complexity for the solution that we have discussed right now. The time complexity for the solution is n log n, because we are performing the usual merge sort by just a little change in the code, while the space complexity for the given implementation is big of n, because we are using auxiliary arrays and n represents the length of the input array. So you can see that this will work fine for the constraints up to 10 to the power 5. So let's create two functions. This is merge sort function, this is merge function. This function is used to recursively divide the given array into two halves. So we are calling this function from our main function, that is count inversions. This function takes in the array and gives me the number of inversions in the given array. So we call this function right from here, and let's see how this function will look like. So here this is a base condition where we find the middle point of the array, and then we recursively call the function merge sort for the left half and for the right half. Then we finally merge after we got two sorted sequences. So let's see how the merge function is working. These are the sizes, n and m represents the sizes of the auxiliary arrays, the left array and the right array. Then we declare two auxiliary arrays that will store the two sequences in the sorted order. Then we declare pointers to these two auxiliary arrays and a pointer to the parent array. Then we copy the integers in these auxiliary arrays, and here we are basically counting the number of inversions which we require. And that's how this answer will store the final answer that we need. So this is the implementation in C++. Okay, so this is the implementation in Java, and this is the implementation in Python. So that's all for this video. If you like the video, then make sure to spread the word. I'll see you in the next video.